This is the second video about pH and POH. In the last video, we defined acidic solutions as one with a hydronium concentration above 10 to the negative 7th, and basic solutions as ones with hydronium concentration less than 10 to the negative 7th. So in this video, we're going to turn those numbers into pHs. So these numbers are super awkward. It takes forever to write a number in scientific notation, and it's kind of difficult to interpret because it's super duper small. So we're looking for a different option to use. So these numbers, they're awkward. We don't like them. We like numbers that are between 1 and 10. Those are easy to talk about. So what we're going to do is we're going to transform these numbers using a function called the P function. Use the P function to transform the numbers into small positive numbers. It is just easier to compare numbers when they're between 1 and 10. Okay, so the mysterious P function is simply this. If you take the P function of something, that means you take the negative log of something. We just called it the P function because it's easier to write than negative log. And we use the P function to help adjust these numbers. So these numbers were for H3O plus, or we can simply write H. So the P function of H is the negative log of our H3O plus concentration. So that's really helpful. So let's go back and transform the numbers that we had here. So if we take the negative log of this H3O plus concentration at neutral of 1 times 10 to the negative 7th, we get a pH of positive 7. Note how the exponent matches the part of the pH value. So this is going to be a hint as to what the pH will look like. Okay, we can do the same for acids. For acids, the pH is going to be less than negative 7 because we took the negative log. So the number is going to get smaller as this number gets bigger. And for bases, the pH is going to be greater than 7 because as this number gets smaller, this number gets larger. Let's take a moment and write that out because that's pretty weird. I feel kind of weird about that. So this column, where we were looking at the concentration of hydronium, the numbers went from large to small. The acidic numbers had the larger numbers, and the basic numbers had smaller values for the concentration of H3O plus. And over here, when we talked about pH, the trend was the opposite. The numbers were smallest at the top, acids, and largest at the bottom for bases. So just like we said over here, the concentrations of the hydronium and hydroxide are inversely proportional. So when we take the negative log of something, the negative log is inversely proportional to the P function of that thing. So as the concentration of hydronium goes up, the pH goes down. So try and keep that straight as we use the pH. The small pH numbers are acidic. The large H3O plus concentrations are acidic. Okay, let's return to the P function because we can use this P function on other things that we don't want to have to write scientific notation for. We can use it for the concentration of OH minus. To talk about that as a nice friendly number between 1 and 10. We can find that by taking the negative log of the OH minus concentration. We can even use it on K, on our equilibrium constant, because this is a really crazy number that can be hard to work with. So we can take the negative log of our equilibrium constant to get pK. That's important. We'll put that in a box. So basically, anytime you see a P in front of something, it means that you take the negative log of that something to find the value. And just like we talked about up there, the POH is inversely proportional to the OH minus concentration, and the pK is inversely proportional to the K. Why not? We'll just include this for completeness. pH is proportional to 1 over the hydronium concentration. So I cannot emphasize enough, inversely proportional. As one gets bigger, the other gets smaller. Okay, we have one more trick we can do with the P function, and then we'll summarize all the things we've talked about here about the P function and pH. There we are. So we have one more P function trick, and that is that we can apply the P function to our entire K expression for water. The equilibrium expression for water is H3O plus times OH minus. We can apply the P function to that entire thing. So we take the negative log of both sides, the negative log of KW on this side, and when you take the negative log of something that's multiplied, you end up with the log pieces added together. So we have negative log of H3O plus, that term plus negative log of OH minus on the other side. Okay. And then we gave some special names to some of this stuff already. So we can substitute in those special names that we did on the previous page. So we named this thing pK, or in this case, pKW for water. We named this thing the pH. And we named this thing the POH. And for our final pièce de résistance, we can substitute in the value for K at 25 degrees Celsius, 1 times 10 to the negative 14. So if you take the negative log of 10 to the negative 14th, you will get 14.0. So for a system at 25 degrees Celsius, the pH plus the POH equals 14. So this is really useful. This is going to allow us to convert between pH and POH without having to take the negative log all over again. And so now we've talked about several different uses for the P function and several different kinds of pH values. So let's make a picture to help us connect all of those different things together. So we are going to connect the pH, the POH, the concentration of hydronium, and the concentration of hydroxide, because those are all the different variables we can use to give us information about how acidic or basic a solution is. We could give you the information in any of those 4 forms, and you should be able to convert between them. So let's look at how we can do that. Let's start with the one we just did because it's freshest in our memory. So we can convert between pH and POH by adding them together to equal 14. So we'll draw a connector line here, and we'll say we can convert it by using pH plus POH equals 14. Okay, and then let's do the one on the opposite side, because we know how hydronium and hydroxide are related because we used it up here. So the Kw, which is equal to 1 times 10 to the negative 14th at 25 degrees, equals the product of these two concentrations. We can convert between these two concentrations using this tool. And then we know how to convert between these two because we used it up here to solve. So to convert between pH and hydronium, the pH is the negative log of hydronium concentration. And a similar rule over here. The POH is the negative log of hydroxide concentration. So now we can convert between any of these four things using these formulas we have written at the outsides of the square. I invented that square myself, so I'm rather proud of it. So now let's make sure we know how to use all these different formulas by doing a couple of quick examples here at the bottom of the page. All right, so we'll move that up so we can still see the square. First example, find the pH of a solution with POH equal to 2. So that means we are located here, we know the POH, and we want to get to here, the pH. So we're going to use this formula to convert between the two. pH plus POH equals 14. We'll insert 2 in for the POH. Subtract it from 14. pH equals 12. Okay, so far so good. Let's do this one next. Find the pH of a solution with the hydronium concentration of 1.2 10 to the negative 4th. So we are here in the square at hydronium. We want to get to here, pH. Again, we only have to move one step around the box. So we can use the formula listed on this side. pH equals negative log of hydronium. And hydronium was given. So we can substitute that, take the negative log. We should get 3.9 as our pH. Okay, so far so good. No sweat. This one over here is a little bit more challenging. Find the pH of a solution with the hydroxide concentration of 1.2. So we are here at hydroxide and we want to be here at pH. So it's on the opposite side of the square. We're going to have to take 2 steps to get there, but we have 2 options. We can either go to the POH and then go to the pH, or we can go to the hydronium concentration and then go to the pH. And either one of those ways will work because that's how math works. So our first option is to use POH equals negative log of hydroxide concentration. So we know this. That comes from the problem. And we can solve for POH. So we can get to this spot, and then we can go across to the pH using pH plus POH equals 14. And this number that we get from this equation can be substituted. We'll solve for our pH. Problem. Okay, and we can do our second option is moving the other direction around the square. And that is to take the bottom step first. 1 times 10 to the negative 14th equals hydronium concentration times hydroxide concentration. We know hydroxide, that gets substituted in here. We can solve for H3O plus, and then we can use the left side of the square. Next, pH equals negative log hydronium concentration. Take that number we solved for and plug it in and solve for pH. So both of these numbers should give you the same answer. And hopefully, if you and your calculator are working well together, that answer should be 10.1. So would highly recommend committing this square to memory to help you figure out how to convert between these 4 indicators of acidity and basicity. So this has been a discussion of how acidic or how basic a solution is. And the next video, we'll talk about how strong or weak an acid or a base is and how those are related.